Yeah, you should be set then, yeah. But if you don't mind, just. That's it.
Take over this? Yeah, sure. Is he here? All right. You can get a headset. Okay. Hi everyone. The 5 people here and folks on Zoom. Okay, 6 people here. Sorry, I lost count. Today we'll be holding lab 4 on computing derivatives and autograd, which is a technique using many modern machine learning libraries, and it will help you complete your homework 1 autograd. Today we have Andy here. I'm Leo, and Alex is from Kigali. He should be on Zoom. Our lab today will mainly consist of 3 parts. First, we'll go through the math, and then we'll go through the principles of automatic differentiation, and finally, Andy will take you guys through a notebook on how to actually implement it in NumPy. Alex, are you here?
Yes, I'm here. Can you hear me?
Yeah, we can hear you. All right. So, Alex, can you take over?
Okay. Cool. So as you said, today we're covering derivatives and autograd. So just as a quick recap, when trading with backpropagation, you typically iterate through these 3 steps. So one is the forward pass to compute the model outputs at the current time step with the current parameters. Next is to compute the derivatives. So the derivatives tell you how much you need to change the model parameters. And lastly is to run an optimizer, which is updating the parameters. Next slide. Okay, and this is how it is more formally. So this is actually quite similar to what you have in the lecture 5 notes. So what we're focusing on today is what's highlighted in red, how to compute these derivatives in a way that's 1, generalizable, 2, efficient, and 3, it's exact. So those are some good requirements of a good means of computing derivatives. Next slide. Okay, so now we'll go over the methods of differentiation. Just for illustration purposes, this is a simple network. So we'll have an input neuron X, a hidden neuron H, and an output neuron Y. So the weights and biases are W and B, and we have a sigmoid activation. So this is just a simple network to set up the problem of differentiating this networks. Next slide. So how would you do the forward pass? So for the hidden layer output, you take the input multiplied by the weight and add the bias, and then feed this through the sigmoid activation, and you end up with your hidden layer output. Then you take the hidden layer output and then feed it into the output layer, right? So it would be hidden layer output times the weight of layer 2 plus the bias, and then again feed this through the last sigmoid, and you end up with your Y, which is the output of the network and output of the last layer. So now that you have the model outputs, what do you do next? One method of going about this is hand coding the derivative. So this is quite similar to what you're doing in the P1s. So you'd take some like pen and paper and then actually compute these derivatives using just calculus rules. So you'd find the reduced forms, try to discretize it as much as possible, and then hand code this into a forward method and a backward method. So next slide. You can probably guess some pros and cons of this. A pro is that it's exact. You're not approximating the derivatives. And if you implement it well, it's pretty fast, right? Because there's no other, you're not trying to do anything else beyond just the backward for that specific function. The cons is that it's error prone and it's really wasteful, especially if you want generalizable functionality. For example, if there's a discrete step that's in that backward method, you won't be able to use it elsewhere, right? And it's also time consuming to code, as you probably noticed from, for example, like P1 batch norm. I think we got a lot of questions about that. And it takes quite a lot of time to transfer the symbolic equations into code for both forward and backward. And now let's look at another method, which is numerical differentiation. So here you're trying to approximate derivatives using finite differences. What it really is just slightly perturbing the inputs and then observing the outputs. And if you do this many enough times and with the right step size, with the right small perturbation, you should be able to learn the slope. You should be able to learn the derivative. A good thing about this is that it's easy to code, but the choice of this small value, the small step size affects the accuracy. And typically you won't get exact results, but you'll have results to within some expected margin of error, some tolerance. And since you're iteratively trying to approximate this derivative, it's also very expensive computationally for high dimensional problems, which are today, like all problems that are useful are high dimensional. So it's also not a great method. Next slide. Just to recap, so neural nets are just nested functions, right? They're universal function approximators, but they themselves are also just a bunch of nested functions. So for example, if you're taking your input X through some layer, let's say F1, you compute that output and then feed it through the next thing, which could be an activation, and then through the next layer. So it's best thought of as just a series of a complex nested set of functions. And how do you differentiate nested functions? So you use a chain rule, right? So in one case, you're starting from the input going out, and for differentiation, you're starting from the output going in. So this is what the next method, which is automatic differentiation, leverages, because you already know that this is how chain rule is done, right? It's from the output side going in. And so next slide. Yeah, so this is a big thing that automatic differentiation leverages. And how does it typically work, right? So you have your forward pass, where you're trying to not only compute the outputs, but also to track operations and intermediate steps, and also intermediate variables. So you take your data, your input X, and then instead of applying like a more complex function, you break it down into simpler operations. Like, for example, if it's like a tan H, instead of just doing a tan H, you compute the individual steps, like the exponentiations, the negations. In this case, breaking it down into small operations. And then you track these operations, you track the computations and store them in a computational graph, which will keep track of not only what operations are being done, but also the intermediate results. And also the intermediate variables, which will be used in the backward pass. And next to backward pass, so in the backward pass, you have this sort of graph or a list. In this case, for the homework, we'll be using a list, but it's a list that has the set of primitive operations that are used in the forward. So now you'll start from the final output and then apply chain rule backwards to each of those primitive operations. So at each step, you're propagating the gradients through the reversed set of operations that you did in the forward. You'll also use the values, the intermediate values that you stored from the forward pass, and compute gradients. And once you have the gradients once you have all the gradients, you now update the parameters. So it's a much cleaner way that uses, it allows it to be, it allows code to be very modular and to be as minimal as possible. For example, if you look at like PyTorch code, you don't have, as long as you use PyTorch functions in the forward, you won't have to do a backward because all the primitive operations that comprise the functions used in the forward they have the backward methods are defined. And again, they're just primitive operations. So like a small function instead of a complex function. And this allows it to be exact and also just as fast as if you had hand-coded the code. Next slide.
Okay,
So
now
yeah,
thank you, Alex. Okay, now we'll dig into the more principles on automated differentiation. So the first thing we want to look at is to building a computational graph. So here the example we have is y equals to f of two variables, x1 and x2. This is just for example, it's not what you'll actually see in neural nets, but then we're just using it for illustration. So how do you build a computational graph? First, you will have nodes that would represent your input. In this graph will be V1 and V2, and you also have the final output of V7. And then basically what we're doing is to add the intermediate nodes that denote the different operations that we made. So as we can see, for the first part of the function, which is taking the log of x1, we will have our node v3, which is taking the log of x1. And then for the second part of the function, we'll create a new node v4, which is the multiplication of x1 and x2. We'll add it to v3, which is the log of x1, creating another intermediate node x6. And then for the third part of the function, we have the sign of x2, which is v5. And then finally, we negate the 2 to get v7. And the forward pass is pretty simple. We just calculate everything. Now, there are actually two ways to do automated differentiation. The first one is forward mode, which is more intuitive. So this is basically how you're going to do it if you're taking this as a math problem, right? So what we're doing is basically for each node, we will compute the derivatives in the forward pass. So for instance, if we take a look at V3, okay, so Vi dot is the derivative of Vi with respect to x1, so we don't really care about x2 here. I'll explain a bit more why we're doing this later. So this is pretty straightforward. So for each node, we'll just take a look at its relation to V1, to x1, and then just take the derivative. So for instance, for log, then we have the node v3. We'll simply take the like 1 over x1, right? So this is typically how we do derivatives. And then for x1, x2, which is the node v4.
Can you turn the volume down a little? It's really loud.
Yeah.
Okay, I'll just. Can you guys still hear me?
Yes.
Guys on Zoom, can you still hear me?
No.
Yes.
Okay.
Can you turn the volume on the speakers down a little?
Turn it down. I turned it down.
Okay, thank you. Okay, anyways. Okay.
That's better, yeah.
All right. Okay, so if you take a look at V2, which is essentially the node x2, since it's irrelevant to x1, the derivative will just be 0. And then for V3, it's just the derivative of the log, which is 1 over x1, or here, since x1 is V1, we'll take 1 over
Hello guys, we can't hear you clearly.
Hello?
Can you try to get closer to your laptop, maybe?
No,
I'm
no,
pretty sure we're using this.
you just stand in front of the gooseneck right there. You're fine right there. It should be fine.
Hello? Can you still hear me?
Not
we
well.
can
Not well.
hear
We can't
you,
hear you
but-
well.
But the other guys, I think I can hear some noise. The other guys, not the TAs.
I try again.
Yeah.
This isn't.
Hello?
Yeah, it's okay. You are using the microphone. It's fine. But the other guys who are not the TAs, we can hear some echo.
What?
What you mean you're hearing?
Echo. The other guys in class, not the TAs.
Oh. No, when we talk, they hear echoes in person.
Wait, it's my echo, right? No one else is talking.
I think the microphone that's listening to the class is a lot louder than the one from the instructor's side.
Oh, so the built-in microphones in the classroom is creating the I don't understand. What?
We don't speak it.
All right, you keep talking.
Okay.
I think that's fine. Is that fine in here? Yeah. All right, then.
Okay. Right. Back to. Sorry, someone has a question or whatever. Hello?
No, we're just gonna say that's fine now. So keep on.
Okay. Okay. Great. Where am I? Okay. Yeah. Right. So in this forward mode, basically, we're going to compute the derivative whenever we get to that node, and then using the train. Wait. Why am I? Okay, yeah. So we're going to compute the derivative in the actually during the forward pass. So this is not we typically see in neural nets, because when we introduce neural nets, you do the back propagation after your forward pass. But this is like one of the ways to do automatic differentiation. But this method has some issues. And so what we usually use actually is reverse mode automatic differentiation, and we'll take a look at why. Okay. So the problem with forward mode automatic differentiation is that for each variable, you'll need to go through the automatic differentiation to take the derivative with respect to this variable. So if we take a look at this graph again, this first forward pass, we can only compute the partial derivatives with respect to x1. And then to calculate the derivatives for x2, we'll need to go through the entire process again. And the problem with this is that in machine learning, we usually care when the dimension of our input is a lot larger than the dimension of our output. So no matter if we have visual data, audio data, like the output can just be a label or like a token ID, depending on your task. But then the high dimensional input means that we can't afford to run through forward automatic differentiation for each input, right? So this will work fine if we have less input and more output, but then in the case that we actually care about, we can't really use this. So we need to introduce reverse mode automatic differentiation. Okay, so for reverse mode automatic differentiation, we will start from the output node V7. And then this is the typical back propagation that we see. So for V7, we have the two input nodes of V7 are V6 and V5, and the operation is essentially negation. So if the incoming derivative of the final output is 1, we're essentially going to just multiply it by 1 for V6, because it denotes the first entire part of the function. And then for the second part, it's just taking -1. And then since we're adding V3 and V4 to V6, so their derivative with respect, their derivative incoming to V6 will also be just 1. And then for V5, for V2 with respect to V5, since it has a its input is its output is both V4 and V5, so we'll need to take account of both derivatives. So if we need to take the derivative of both nodes and adding them, so that gives us the final derivative for x2 or v2, and then for v1 we will do something similar. So the advantage of this method is that in one forward pass you can essentially compute the partial derivatives of all inputs, which is what we want because we have like a higher dimensional input than output usually. Okay, and now this graph is essentially kind of more complicated than what we actually implement, because in actual modern libraries we may like have different optimization techniques that we want to use, but then in homework 1 autograph we'll just use a list of input operation, etc., to build kind of a sequential graph. So we don't have like all these divergences. Okay, so now I'll talk about the two kinds of graphs that we build, the two kinds of computational graphs. The first one is static graphs, which is built before execution. So before the forward pass, you already know what operations you have, and then you're going to build this graph like before you actually run into the computation. So the pros of this method is that it's easier to optimize because you can like see some operations that if they happen more frequently, you can say merge those two operations into a new operator, and then that will lead to better performance. But then the disadvantages is that it's less flexible, and then it's harder to debug because first, you can't like run anything before you build the entire graph. So if there's a flaw in your graph, you'll need to like go back all the way again and rebuild your entire graph. And if you have like these optimizations that you want to use, then it will be like even more difficult. So okay, let's first take a look at the second method, which is dynamic graphs. So this is built like during execution. So during the forward pass, it will build each node as you go. And then this is a more flexible method and it's easier to debug, but then it will be slower than the static graphs because since you're building it on the fly, it's harder to perform these operator fusions and other optimization techniques that you may want to use. And this is a diagram illustrating the two kinds of graphs during execution. So the first one is static graph. So you first create the graph, you perform some optimizations, and then you go through your computations of forward pass, backward pass, and then finally you update your parameters using a gradient descent or some other methods. And then the second one will be the dynamic graphs, which is you have your initial node, which is essentially your input. And then during your forward pass, you will compute the intermediate results, and then you build your computational graph. And then afterwards, you do your backward pass and update your parameters. And after this iteration, you will destroy your graph, and then you will build a new computational graph depending on your new input. Okay, so nowadays, actually, most frameworks use dynamic graphs because it's easier for researchers and learners like us to like take it apart and then build a new computational graph. And then the frameworks that use static graphs like TensorFlow 1.x, which is like a while ago, and Caffe, these are mostly used in industrial settings because in those cases, like the computation doesn't really change once it's settled, so it's easier for them to do all sorts of optimizations to enhance performance. All right. And for additional readings, you can either take a look at the deep learning systems course here we have at CMU and other machine learning system courses. They'll dig deeper into automated differentiation. And then you can also take a look at repos of JAX and other machine learning frameworks, PyTorch, TensorFlow, all that. And then finally, there's a survey paper on automated differentiation that you're welcome to take a look at if you are interested. Okay, and now we'll go through a notebook.
Okay, nice.
Can you guys see clearly? No?
A little small.
It's a little small. Any better? This is the best I can do.
Yeah.
Okay, that's nice. So this is first. I'm just gonna discuss what is the flow of this notebook. So firstly, there are three major tasks that you are going to like finish in the homework one part one AutoGraph. Firstly, you need to build a AutoGraph engine that contains the forward add operation functions and backward method. And the second task is to implement the backward operation functions for some basic operations like add, sub, multiplications, etc. And the third task is to like build the modules with the differential with the autodiff engines you built before. And in this notebook, I will first introduce three classes, Python classes that you are going to play with in this assignment, so you know the context of this assignment. And then I will walk through the rough ideas of three tasks with like simplified pseudocode and give specific examples for some parts. So Leo and Alex has introduced so many examples. I'm going to use a very, very simple example here throughout the notebook, which is just h is equals to x times w, x times weight, which is just a matrix multiplications, and then y is equal to h plus b. H plus bias. So there are two operations here, a matrix multiplication matrix operations and addition operations. So firstly, there's an operation class that stores the basic informations of your operations. So I don't think you need to like modify it yourself, but it is good to know it. So it just takes the input of your operations, the output, and the gradients to update. The gradients of update, this will store the parameter gradients if for the gradient to update that needs to be stored internally throughout the autodiff engines. And the backward operation is basically the backward version of your like operations like backward additions or backward multiplications, etc. So this is a very simple examples of, this is the code example of the example I used before. So if you want to add the operations like h equals to x times w, it's gonna be like, the input is gonna be x and w, and the output to update is none and dw. So there are two things to remember. The first thing is that the length of gradients to update needs to be the same with the length of the input. And for variables like x and h here, we because they are not like changeable parameters like weight and biases, so we just store them internally. That's in the gradient buffer class we're gonna see later. So it is none here, but we need to like place a placeholder here just to maintain the shape of the gradients to update to be the same as the shape of inputs. And the second class is also a built-in Python class that you're gonna play with for this assignment. You also don't have to modify it yourself, but you have to be familiar with some functions of it. So these are three functions that you're gonna play with in this assignment. They are like pretty straightforward, but I think the name of them are somewhat misleading. So basically, the gradient buffer just has a dictionary as the data structure for memory. And the add spot functions is like add the zeros matrix with the shape of input array into the memory. So remember that it's adding a zeros matrix instead of just adding the array into the memories. And the update parameters, it's called update, but it's actually just add the gradients to the NumPy array. So this is also somewhat misleading too. And there's a set parameters, which is like let the values of arrays equals to the gradients input. So here's a very basic examples. So you can see that there's an X array and gradients of X as inputs. And if you add spot X, it literally just creates a zero matrix with the shape of X into the memory. And then you updated X with gradients of X, which is added the gradients of X into the X arrays. So you can see that the matrix printed out here is just 0.1, 0.2, and 0.3, which is the zero array plus the value of gradients of X. And next example is like, and the following examples are pretty much the same. So you don't have to call the clear functions yourself, but it's just good to know. And the last one is just the autograd engine that you're gonna build. There are two class attributes, which is the gradient buffer that is an instance of gradient buffer class that used to store the mapping between input data and their gradients. So this stores the parameter that's internally. And there's also an operation list in this class that stores all the operations added when you like in the forwarding functions of modules like linear or activation functions or loss. And the class methods are also pretty simple. So there are two methods that you're gonna implement, which are add operations, which is just add the operations class to the operation list. And the other one is the backward, which is used to kick off the process of backpropagations and traverse the operation list in the reverse order and calculate the gradients at every node. So we are also doing the backpropagation in reverse order, and we are trying to implement dynamic auto-differentiation engines. So there's an important note to know here. So parameters like weight and bias need to be updated during the optimizations, while the non-parameters like input and attributes like intermediate variables don't need to be updated constantly. The value of the gradients of them are only used for back propagations. They don't need to be updated. So for inputs that are not parameters, we want to track their gradients internally using the gradient buffer. So remember, inside the auto engine class, we have a gradients buffer to store all these variables. And this allows us to propagate gradients backward through the computational graph. Like for parameters of the networks, like the weights, we don't need to add them to the gradient buffer because their gradients will be updated directly in the backward method using the gradients to update list. And first, I'm gonna go through, so like actually before entering the implementation walkthrough, I just want to spend like, I just want to explain very briefly about how these things work. So basically in the like hard-coded way, like normal homework 1, part 1 method, you just like implement the forward method and the backward method of each modules. Like for linear, you have a forward, you have a backward. But in the case of auto differentiation engines, you create an auto engine instance first, and then you pass it to to your modules like linears. And during the forward pass, it will like do the forward, do all the calculations of forward pass, and at the same time add these operations to the operation list inside the auto differentiation engines. And the auto differentiate, and it doesn't have a backward method itself anymore. The auto differentiation engines will take care of the back propagations. Okay, so this is the first function you're gonna implement. It's just add operations during the forward pass. So it is pretty simple. There are two to-dos. First, you need to add all the inputs to the self-gradients buffer, use the add-swap functions, as I explained before, and then you just append the operation object to the operation list. So it is going to be used in, the add operation is going to be used in the forward pass of your module. So this is the procedural code. It's like just maybe 5-6 lines of code. It's pretty easy. Yeah. And the next is the backward propagation, which is backward functions of auto-diff engines, which is a little bit complicated than the add operations, but it's still pretty straightforward. So first you need to iterate through the operation list and propagate the gradients. And the second task is for the first iteration set the gradients to be propagated equal to the divergence. So the first gradients of outputs you enter is going to be the divergence. It's going to be the input of these functions. And then you just execute the backward for the operations and loop through the inputs and their corresponding gradients. So also you can see in this procedural code, you can just go through the operations inside the operation list in reversed orders and calculate the gradients of output. So remember that we have a gradients buffer inside to internally stores the gradients of value we needed. So let's going back to Leo's PowerPoint. So take an easy example. When you go in reverse order, when you try to calculate the V6, you already got V7 calculated, so you can just directly use it from the gradients buffers. So that's why that's one of the reasons we go in the reverse orders. And also the meaning of these lines of code, you can just use the get parameters method to get the gradients of output you want from the gradients buffer, because by the time you calculate V6, you already have V7 ready in the gradients buffer. And finally, you need to calculate the gradients of input, which is just go through by the backward operations of your operations in the list. And then you update the input, and you update it for two cases. So as I mentioned before, there are variables that you need to store internally, which is the input value, the intermediate value, etc. And there are also some variables that you need to update it with the autodiff engines that is stored externally, like the weight and biases. Yeah, this is examples. So for H, it is intermediate variables. It needs to be tracked internally. So we update the gradients buffer of H. And for B, it is externally tracked. So we updated the gradients to update by one. This is just a simple example. The one is because we use divergence one and divergence one as input as the divergence. Yeah, and the next task is to define the backward functions of some basic operation. It's extremely simple. These are just two very, very easy examples. So for backward functions of additions, you just so you can consider if y is equals to h plus b, and consider the partial differentiations of dy dh and dy db. You will know that the weight is going to be 1, so it just returns the a grad and b grad, which is just the grad output times the non-pi ones of a. And it's also the similar case for x backward. And the final task is to like build your own modules in auto differentiation engines ways. So basically, as I mentioned, take the linear module as an example. The initialization method is like built in for you. You don't have to modify it. So the forward method, think about what you need to do to implement this forward method. You just need to like do the normal forward calculations, and at the same time, you add the operations into the operation list of your AutoGrad engines. So it's also simple. And I think building modules like worth the most points in this assignment, but I think as long as you can like implement the backward method and add operation method of autodiff engines, these are just like 3 points for you. It's just only maybe take you like 10-20 minutes of time. So yeah, I highly recommend you to give it a try, and I think you have a good chance of finishing like in an hour or so, because yeah, it really gives you a lot of hints, and yeah, this is it. Thanks, guys. So this is all I have. It is not a long assignment as well, so yeah. Do you guys have any questions regarding the homework or anything else? Check if there's questions on.
Oh yeah. I don't think I can see the Zoom page on my end. I don't think so. No.
Okay. You guys go to the. I'm trying to look at like the chat.
Yeah.
What do we have to submit an AutoLab?
For AutoGrad 1?
No, on the AutoLab for the bonus.
Oh, it's the same for the
Here you go.
and
You can look at it right there. I don't think anyone has any questions, but. So, is this the same assignment as that or no?
Yes.
No. They're separate. There's one called bonus. There's one called AutoGrad, but they are considered as the bonus part of part 1.
It's just the bonus asks you to like implement new modules, but then you're essentially using the same logic as homework 1P1. But AutoGrad asks you to like redo stuff you are doing in P1 with automatic differentiation. So that's like the difference between the two, but then they're both bonus assignments. And they're due, I think, once a week.
And what is this? This is the same content, is that right? Or
Yeah, you're implementing the same modules that you've already done in homework 1P1, but we ask you to build it using automatic differentiation.
no, that's not my question. I answered that.
Okay.
What, do I submit this somewhere or no?
That's just the recitation.
Yeah.
You don't submit recitation.
Yeah, the assignment is on AutoLab. You just do it normally there. This is just for illustration purposes.
Can you see the chat?
There seems to be.
Okay. That's nice. Okay, so we still got some time, but we can just let you guys go. If you don't have any more questions, just come to my office hours if you met some problems during the implementation process. Other than that, thanks for coming.